This slide here shows all of the 12 cranial nerves going to the head. The 12 cranial nerves coming to here, there's some ways that neurologists and physicians can actually see them and see how functions are actually occurring. It's all the organs you see here is all the distribution. You do not need to know all these specific nuances. However, we're going to show you several of them which you can now see, and now we're going to give you, through this DVD series, a thermometer you can use at home to look carefully at your children and do what the doctors unfortunately have not been doing. Because as you will see when we show you the patients here today in this video series, you will see that some of the features, when they happen, you can see them with your own naked eye. These are medical emergencies. Your child is having silent ischemic strokes and you did not know. But if the physicians were doing their job properly and looked at the children neurologically before they put a vaccine in them, because a vaccine is like a surgical procedure, had they been doing that and brought the patient back a day or two afterwards, the features you now see, the doctors would have picked this up a long time ago and we would have said, wait a minute, we have a problem here. That's unfortunate. We can't correct what we have done from that perspective, but we can do things differently in the future. And I want to give you the tools so you can see for yourself and be able to monitor your children in ways that actually you can see something's going on when your child is not complaining, when your infant's not complaining, and if you're an adult, when you are not complaining, when the silent damage is happening to your body. It's a medical emergency and how it can be treated. Here we have a series of the arterioles in the very top here, the flat plate, and then beneath that you have the pipes coming down here, which are penetrating arterioles. You see the small finger branches coming off. These small fingering branches are the critical areas that are losing blood flow in the sledging process from mast and zeta and immune hyperstimulation. You can see it here. In reality, in the real world, we cannot see this going on, and because we cannot see it, we never know what's happening. But it's causing profound damages to the body and the brain and impairing function and behavior and emotions and sensation and all the factors neurologically we ascribe that separates us as humans from the rest of the animal kingdom in very subtle ways. And at the bottom part there, you saw two examples of stroke. So here, this slide here now is very, very critical. This was published in the medical journal Stroke by Torvik. And the outline you see here, the hatched areas across this brain. Now the brain's focusing, looking this way, and the eyes would actually be right in the front of the brain, and the temporal lobe is down here. But the gray hatched areas are areas which are common watershed vascular areas for all of us, by and large. This is a commonality to the top of the brain, kind of like an inverted C. This is the area that ends to be damaged in Alzheimer's disease, and there's a reason for that. And then down the lower part of the temporal lobe here is an area that many autistic children have problems with, processing of faces and integrating things they see in the environment and focusing in on certain features. This is a watershed area. And back in the little sort of like hub in the back of this image here is what we call the cerebellum. And the cerebellum is responsible for coordinated motor movements in response to tracking objects in space, as well as to adjust your physical posture relative to things that move. Coordination problems are common in children, and to a certain extent, we've now begun to see in the neurosciences that also in some subtle ways, the cerebellum is involved in attention of all things. And so you can see how all these different areas vascularly are separated from each other. There's some commonalities, however, at the individual level, there will be individual differences and variations. And because of those individual differences in the blood watershed areas, in vascular territories, and the degree of collateral circulation to various areas, you can get a whole range of no deficit to profound deficit, and everything in between fits in the same pathological model of causation. So, whether you have attention deficit disorder, a specific learning disability, autism spectrum, Asperger's, social problems, memory problems, attention problems, concentration, sensory, the whole gamut of range of possible problems, as well as range of severity of the symptoms you have, is a function not only of the vascular networks, but also the pathological process happening, when it happens in development, how long it lasts for, whether it's reversible or irreversible, waxing or waning, or permanent or non-permanent, and how long it lasted. Those are a huge number of variables that is difficult to predict in any way that we use science for. Science cannot predict things in a consistent way, in replicable ways, when the very thing it's trying to measure, we call these dependent measures, varies by so many multivariates. We cannot control for it. And that's why we find nothing, because we don't really know what to define as our measuring point, which is why a lot of this has been difficult for us to find. This slide here describes transcortical motor aphasia. A famous neuropsychologist first published work on this stuff, and we realized that a transcortical motor aphasia, big fancy neurological terms, is due to a stroke. But more specifically, Norman Geschwind, the first to really report where the areas in the brain are responsible for this and why it was happening. This is something we see in all these autistic children, by and large, in varied degrees. One is speech production is gone. They've lost the ability to make meaningful, expressive speech. But comprehension's intact. You can ask these autistic children to do a task for you, and they comprehend you, and they follow through with it. But however, there's another area here in the temporal lobe called the repetition area, and the repetition area, sometimes these children, individuals, can repeat back to you almost echo-like format, parrot, if you will. They can repeat back exactly what they heard. However, they cannot make that sentence on their own, by their own volition. And this is called a transcortical motor aphasia. When you lose speech production, you retain comprehension, and you retain varying degrees of speech repetition. Now, the only way you can ever create that behavioral syndrome in the human brain is by damaging the small blood supply, because up here, the speech production areas are in a watershed vascular area, which is exactly what Torvik's article describes, and other neurologists and behavioral neurologists and neuroscientists have confirmed that this is going on. So if you damage the microvascular watershed areas in the front of the brain here, you lose speech production. But you retain speech comprehension, and you retain, to a certain extent, repetition sometimes. There's no other way to cause this. So if you see this syndrome in an individual, you cannot say genes cause this, bad genes. You cannot say anything else cause this. The only way you will commonly cause this, by and large, human brain is messing around with the blood supply, bar none. So, to conclude, autistic children seem to have some problem with blood supply based on the behavioral symptoms we see. That's the power of neuropsychology, that's the power of functional localization, and that's the power of integrating these two together. There are some exceptions, but not when you put a lot of people together. So now we're focusing on blood supply. We recognize that. This slide here is looking at blood supply to an area in the middle part of the brain called the thalamus. This is very important for autistic children. This is important for schizophrenia as well. The three fingers of blood vessels you see coming into the area, these are called the lenticulostriate arteries or vessels. They're also called the stroke arteries in the brain. There's reasons for that, but they come from a large pipe to a smaller pipe, and there's a big change in pressure coming down into these things, and they tend to be very susceptible to damages. But why I have this slide here for you is the two small vessels up front of the thalamus, the thalamic arteries. These are very, very critical to when you block off the end vascular territories to these in adults when they have strokes. Sometimes you can get a clot coming off the neck arteries and come up there and get blocked there. This is a profound thing, and the next slide you're going to see is going to be very distressing, and I apologize for that.